Okay, so we're now changing orbits again. So from low Earth orbit to the moon and beyond to the final frontier. So I'd like to introduce our next speaker, our keynote for the afternoon, Dr. Bhavya Lal. Bhavya is a former NASA Associate Administrator for Technology, Policy, and Strategy. Bhavya has a BS and MS in Nuclear Engineering from MIT. And she also has a master's from the Technology and Policy program and a PhD in Public Policy and Public Administration from George Washington University, but that's fine as well. So she's a member of the Nuclear Engineering, Public Policy, and Public Administration Honor Societies, and we are very excited to have you with us, Bhavya, today. So please, thank you.
Thank you, George.
Change the slides with this.
What a great topic for the conference. I wonder if you know this, and I'm sorry I came a little bit late, so I don't know if this came up. You have Scott Pace here. Scott Pace is the father of Artemis. He created it. He birthed it. So my role here was, while Scott Pace gave birth, I was the one who was over-caffeinated, postdoc, intern, who kind of made sure that the toddler didn't run off and the program didn't get canceled during nap time. So I was in the Biden administration trying to make sure that Artemis continued. And I just think it's awesome that two MIT alum are involved in a program that is so important for the country. So I'll be talking today about power. I am a nuclear engineer. And a quick way to relate it, and I'll come back to it, as you know well. The lunar night is 2 weeks long, and the temperatures plummet to 250 degrees, minus 250 F, right? So this is the kind of stuff where electronics will freeze within minutes, forget humans. So any material is frozen solid. So we need nuclear power on the moon. We need nuclear power to go to Mars. We need nuclear power on Mars. We need nuclear power beyond for science. So that is what I will be talking about. So the three things are, why do we care about nuclear systems in space? And again, if they are so awesome, as I'm sure you all think, why don't we have them already? And then, of course, the last question is, well, so how do we get there? Just to level set, and I'm going to be making sure that I can see my slides. So just to remind you all, nuclear power isn't just one thing. There is radioisotope systems. It's basically a hot rock, and there's nothing. Plutonium-238, it decays through alpha decay, and you generate heat and electricity. And then there's fission systems where you deliberately fission atoms, nuclei to produce power. And you can use highly enriched uranium, or you can use low enriched uranium for doing that. On Earth, all of our power plants are actually, most of the commercial terrestrial power plants are low enriched uranium. And so when we talk about space, though, what are we talking about, and what am I focusing on today? And again, there's a lot going on this chart, but all I want you to get is, the rightmost is basically fission surface power, which is essentially a power plant as you know it on Earth. In the middle, you have nuclear electric propulsion, NEP, which is basically you attach thrusters to the back of power generation. So you generate electricity, and the electricity powers the thrusters, which moves your rocket. And the third one is nuclear thermal propulsion, NTP, which is essentially a chemical rocket, except you've separated out the heat source from the propellant. Chemical rockets, oxygen, hydrogen combine to produce the heat, which gets the water vapor to go out the back at high speeds. Whereas in NTP, you heat the hydrogen, or whatever your working fluid is, which goes out the back. So just kind of making sure that when I say FSP, NEP, NTP, you know what I'm talking about. And then, of course, there's fusion, which is fusing nuclei, but we won't be talking about that today. So again, why do we want nuclear power in space? Well, there's kind of two big buckets of scenarios. When the solar flux is really low, so you're out, beyond Mars, you're out in, Neptune, Pluto, you need solar flux is too low, you need the power. Or you need, I mentioned lunar nights, it's shaded. Then there's harsh conditions. So when you're in the orbit of Jupiter, for example, the radiation environment is too corrosive for solar cells, you need nuclear. And then, of course, the other bucket is when you need high density power. So for example, if you want to be doing in situ resource utilization, ISRU on Moon or Mars or wherever, asteroids, and you need a lot of power. You need a lot of power if you have human settlements. And then we won't get into them too much today, but you also need nuclear power for national security applications, whether it's lasers or other high power assets. So in a quick example, the Voyager, which is, I think, 150 AU is out already, AU, astronomical units, distance between the Earth and the Sun. And, it continues to give data. In fact, Voyager was the spacecraft that actually gave us the first indication that there's an ocean beneath the cracked icy surface of Jupiter's moon Europa. And of course, last year we launched a probe to Europa. So it's an extraordinarily useful mission we had. And as you can tell, the solar energy flux pretty much disappears being useful after Jupiter. So if you're going to send a mission to Uranus at about 20 AUs, you have no option other than nuclear power. Batteries just don't last long enough. I mean, if you remember, the New Horizons mission was it took 9 years to get to Pluto. Batteries are not going to last. And then, of course, lately there have been emerging new users of nuclear power, commercial entities that want to develop a cislunar economy. A company called Interlunar wants to mine helium-3 on the moon. There are others who want to do other sorts of commercial activity on the moon, and we leave aside the fact whether it's a viable commercial business or not. But there is this new bucket of users that want nuclear power on the moon, on Mars, and so forth. I will just get all of these points. So that's nuclear power. Now we also need nuclear propulsion, and I'm going to oversimplify a little bit, which actually I don't need to for a MIT audience. But NTP gives you more, almost as much horsepower as chemical systems, and a little bit better gas mileage, twice the ISP. And NEP systems give you potentially 10 times the ISP, although not as much horsepower, which may be okay if you're going to to the outer planets, where continually thrusting systems will get you to these places better than chemical systems. And of course, because you have higher horsepower, you can get faster trip times to Mars, or you have, if you're talking about national security applications, what is being called sustained maneuverability. Basically, move fast around, whether it's Earth orbit or cislunar space. So again, hugely important for getting to places. One way I think about nuclear is the counterfactual. What happens if you don't have it? So one thing is that you get a lower return on your investment. So Solar Probe Plus, this is a probe we have, in fact, around the sun. It was originally designed with an RTG, which was taken out. And as a result, the probe can no longer get it as close to the sun as would have happened had it had an RTG. And also, it cannot measure solar winds as well as it could have. So again, hugely expensive mission, and we are getting less for our money because we chose not to use nuclear systems. Similarly, the Huygens mission to Titan, it cost more than $660 million. It had basically 3 hours of battery life. Most of it actually was drained during the descent, and we got maybe 30 minutes of data from the surface of Titan. The Philae lander, the ESA probe that landed on this comet 67 PCG, again, it landed weird, and the solar panels weren't correctly oriented. So basically, we got 60 hours worth of data. New Horizons, again, a hugely successful mission, $700 million. But basically, it didn't have the delta V to go into orbit around Pluto. It just whizzed past Pluto. And we essentially have 24 hours worth of data from New Horizons. And again, expensive mission. So that's kind of one piece, reduced amount of science we get. But it's also reduced speed of science. And again, sticking with New Horizons, it was transmitting data at basically 1 kilobits per second. And as you know well, on Earth, our system, our internet is moving information faster than 100 megabits per second. Basically, the antenna had an output power of 12 watts. And the data rate was further limited because it had to do all sorts of other things. And it switched between sending data back to Earth and collecting more data or processing data. So again, not ideal. And it was, in fact, more than a year before we got all the information back from the New Horizons mission. Another kind of counterfactual is that, yes, you can go to Mars with chemical systems, as Elon Musk recently announced that he wants to send a Starship in 2026, uncrewed, and a human Starship in 2028. Again, not sure if the dates are going to be met, but chemical systems aren't ideal for deep space travel. I think Mars is 140 million kilometers. Hey, a funny thing I just recently learned, if you ask Alexa how far is Mars, it actually takes a little bit of time because it actually calculates how far is Mars on that day, which is kind of cool. I don't know if you guys knew that. Anyway, back to chemical systems. They are inefficient. You need a lot of launches to have the amount of propellant you need to have the kind of delta V you need. And again, because of those reasons, you have to stick to conservative home on orbits. You don't have a whole lot of flexibility. You have fewer abort windows. You're really you have the window of launch is days instead of months, that sort of thing. And then of course you have to do all these complex operations of having tankers and propellant tankers pre-positioned, and they need to connect in the right exact amount of times, and that just makes the logistics fragile and the integration very difficult. And again, it can, you can go to Mars with chemical systems, but the cost is high. You have so much propellant, and there's very little flexibility and a lot of complexity. And actually, even if you do go to Mars with chemical systems, it only gets you one way. You still need to return, and the propellant ideally needs to be produced on the surface of Mars. And in fact, yesterday I met somebody from here who worked on the MOXIE experiment, which is a NASA project to produce, I think, methane on Mars. So, we would need about 1,000 metric tons of propellant to come back, and needs to be produced on Mars. You could use solar panels. Remember, Mars is 1.5 times as far away from the sun, and according to some of the math that folks have done, it'll take about 14 football fields worth of solar panels to produce that kind of propellant. And that's assuming you can do it autonomously and all of that, which we have no idea if we can. And remember the poor little Pathfinder, dust storm kind of shut down. So it is not trivial. So you will require a fission reactor even in a scenario where you're using chemical systems to go to Mars. So this is your little cheat sheet. And actually, I have a homework assignment for you guys. This is kind of old, and I want to know if it's still accurate. So if any one of you technical people, and I see Deva, hello, if this is incorrect, I need to know, because I just think it's just such a compact way of showing why you need nuclear. So I would like to up this chart if I can. And if that happens, my coming to this conference was worth it. OK, so nuclear is so awesome. Why don't we have it? Let's talk about that. So for that, we need to get a little bit of history. So this is actually a picture I took when I was at NASA, and I went to Marshall Space Flight Center. It was like a little thing standing in a corner gathering dust. So everybody remembers the first thing President Kennedy said, and again, I can't do the amazing Boston accent he had, this nation should commit itself to achieving da-da-da, right? He said that. But then he actually said a second thing, that we need to invest in nuclear thermal propulsion. And didn't happen. And if you look at the chart that I took a picture of, you'll see that we achieved, number one, take a man to Mars. It was a man. Moon. Take a man to the moon, bring him back, mission accomplished. And then third and fourth, and I can't read it anymore what that is, but number two, nuclear rocket, still overdue. Again, just a quick overview of what we have. Actually, we started investing in nuclear systems at about the same time the space age started, which a lot of people don't know. So in the 1950s and 60s, the US Atomic Energy Commission, which parts of which are today the Department of Energy, and NASA started a program called SNAP in actually 1965, well before most of you were born. We actually launched a nuclear reactor, with even an experimental thruster on board, which shut down in 43 days, but not because of any issues with nuclear, and we haven't launched anything since. In 1961, we also launched a radioisotope thermal generator, and we have continued to launch RTGs since then, and pretty much every major mission we have had an RTG on, and upcoming we will have an RTG on the Dragonfly mission, which goes to Titan. More recently, we've done some work. NASA continues to invest working together with DOE on fission surface power for the Moon and Mars. And NASA has also worked with DOE on actually doing an experiment called Krusty, where we actually ran a zero power reactor at the Nevada test site. And I got a chance to go see that, and it was super fun. And I don't know if you've ever been to a high enrichment uranium facility where they have for every visitor, they have 2 people who follow you around. It's kind of fun to go to such places. And then there's other efforts as well. AFRL is investing in a program called JETSON, which is about nuclear power. The Defense Innovation Unit has some work underway, and there's actually the really exciting part where there's some commercial companies, both in the United States and other countries, investing in commercial RTGs, which are not plutonium-238 based, and it's pretty cool. So on the propulsion end as well, we started investing in the 1950s. We tested a program called NERVA, and the tests went pretty far, all on the ground. And then, unfortunately, for a variety of reasons, DoD lost interest in space nuclear reactors because solar power was getting well enough. Nuclear weapons were getting light enough that they did not need nuclear power, basically, to both power the satellites or carry them around. And Mars plans were essentially canceled when Nixon came about, and so even NASA lost interest in NTP or propulsion systems. More recently, NASA started a program with the Department of Defense, DARPA, but the program is in limbo, as if those of you who follow this kind of work would know. So this is an inventory. Best we can get the numbers is not very well understood, but in the last 60 or so years, we have started and stopped about 12 programs and spent nearly $20 billion with really 100-watt electric RTG to show for it. That's what we have. We have a 110-watt electric RTG, and it is, as taxpayers, as scientists and engineers, we should be outraged that we have invested this heavily and gotten nothing in return. So what is the reason for that? I think part of it is, in my view, and again, you all may have your own views as well, I think one of the biggest reasons is there has not ever been a strong mission pull for space nuclear systems. Even today, nobody at the head of Space Force or even at NASA is raising their hand and saying, I need an NTP system to go to Mars, or I need cislunar maneuverability, or even maneuverability in orbit. Why is that? I mean, it's probably, some of it is lack of understanding of the role of nuclear, and some of it actually is we have reasonable alternatives, right? Solar is pretty good, batteries are pretty good. There are worries, very legitimate worries that these things would cost a lot, and oftentimes mission planners underestimate the cost of these systems. We did that with a NASA nuclear electric propulsion system called JIMO Prometheus, where we, underestimated the time it would take us to develop systems. And then, of course, there's regulatory issues, and there aren't really very clear rules, although I think that is getting a little bit better, which creates this mismatch between how long we need to how long we need to have a system versus how long it'll take to develop something. And again, it's in a way it's a chicken and egg system. Why is there no mission pull? Because there's no good system that exists that mission planners can say, hey, we got that, put it on our spacecraft. And why is there no tech development? It's because there's no mission pull. So it's kind of this cyclic thing. And just just to kind of look at the Jimo Prometheus example, it was a huge amount of excitement. I think 2002. The program announced, huge promise. We will go, explore the ocean worlds, and this optimistic missions announced. Very aggressive requirements. We'll have 500. We had never launched anything. Well, apart from that 1965 reactor, maybe 100 watts, 100 kilowatts. No. 500 watts, I think it was the SNAP 10A. Anyway, so this is a 500 kilowatt electric system announced, aggressive requirements, and then tech development begins. And then within months, we start falling behind, and they start compromising, start lowering expectations. And then, of course, the mission gets abandoned, tech development stops, the workforce, goes through the wind, and, the infrastructure decays. And this is something that you may even say about the Draco program, which is currently in limbo. It's the same reinforcing cycle of failure. One reason is that, and again, one of the things I'm thinking about right now is what do we need to do to fix this? So one reason may be that there's no clear institutional owner. NASA has interest, DoD has interest, DOE has interest, but no agency owns nuclear end to end. And most programs, for example, the Draco program I've been talking about, tend to be joint programs, and there is no home. Nobody. So for the Nautilus program, the first nuclear reactor for the Navy, Admiral Rickover was he was the owner of the nuclear Navy, and you better do what he says. Oppenheimer for the Manhattan Project, for Operation Warp Speed. I don't know, Matt Hepburn. I haven't really researched it as deeply about if there's one point person. I think there was some Solis or somebody who was the the key person who made sure that there was ownership. And then, of course, because of fragmentation, there's no coordination, decision making is slow, accountability is lacking. So the question is, how do we break the cycle? And again, this is something that there's actually scale up of work. The current administration is actually quite interested in developing both terrestrial and space nuclear systems. And that's actually one thing that is different this time around, that there is potentially budget momentum across defense, nuclear, and space sectors. There's also geopolitical urgency. It's widely believed that China is planning to have a nuclear reactor on its ILRS base by 2035. And then there's commercial companies that believe that they can develop nuclear systems, and you would not know the number of papers I've read that talk about what is the SpaceX of nuclear, and I don't know how real that is, but there's a lot of enthusiasm around commercial nuclear systems, and obviously it goes without saying that in nuclear, as in other areas, whoever is first is going to set the global standards. And for nuclear, it's really important that these be related to safety, operations, and commerce. And we want to be the ones shaping the rules, not others. So one thing that we have been thinking about is we have had so there's excitement. If you watch the testimony of the incoming administrator, he talked about nuclear propulsion as a priority. I mean, he talked about 3 priorities. Nuclear propulsion was number 1, together with Mars. And there's something to be said about that. So if there is to be a crash program, are there any lessons from the past? And if you look at the Manhattan Project, Nautilus, Operation Warp Speed, and even Jimo Prometheus, there's several themes that recur. One of them is, and again, I just have a few, that every success had a singular goal and a central authority. Rickover, Leslie Groves, and Slowey had the power and the accountability to drive results. I mean, when no one's in charge, nothing ships. Another one is Both the Manhattan Project and OWS, Operation Warp Speed, didn't gamble on a single solution. They didn't announce a winner. They funded multiple approaches in parallel and picked winners based on results, not theory. A third one is milestones. Nautilus ran on weekly tests. OWS paid only for deliverables. Manhattan Project tracked critical mass and not paperwork. In every case, progress was measured and enforced. There were no open-ended studies, and contracts were tied to progress or shut down. A fourth one was actually fielding something less exciting but fast. So Jimo Prometheus tried to go straight to a flagship mission, right away collapsed. Both the Manhattan Project and Nautilus built test beds first. OWS ran clinical trials and manufacturing in parallel. The message was fly something small, then scale. A fifth one is stable budgets, not fiscal ping pong, which is what we've done with nuclear systems. Every successful program had protected multi-year funding insulated from annual turbulence. It was in fact budget instability that killed Jimo Prometheus. A sixth one, and again, it's a question mark if it applies very closely, but all the programs I looked at had co-located teams. They had engineers, operators, and safety experts shoulder to shoulder. No, maybe it was the olden days, but no one was emailing specs. They were solving problems together in real time. And the last really important point is fast doesn't mean reckless. Manhattan Project managed unprecedented risk without paralysis. OWS moved fast without cutting corners. Even Nautilus prioritized safety without delay. The model isn't reckless speed, it's disciplined urgency. So the takeaway is that we need structure, we need clear goals, we need empowered leadership. We really don't have it even now, and I don't know how much of that is planned. We need milestone-driven contracts, and of course, the discipline to test, learn, and scale. So if there is a future space nuclear program, right now, the NASA and even the DoD approach is peanut butter spread, right? Let's just fund fission surface power. We'll fund a little bit of NTP. We'll fund a little bit of this, a little bit of that. Strategy means making choices. And that means making some people angry with you. So I propose we focus on propulsion, power before we do propulsion. Power is the heart of whether it's surface power, in-space power, or propulsion. So let's make that choice, put our money in power. Early wins build momentum. Let's do a demo. Why not 2028? The Trump administration is very interested. What can we do by 2028? What kind of a government crash program or even a commercial public-private partnership might work? Let's do a flight program, not an R&D program. All of the current programs that we currently have are essentially R&D programs. Break the cycle. I think we should try something different. We tried 60 years with the government. Let's try something commercial. Why not? Fleet approach. So we are used to building Battlestar Galacticas. Let's build some drones. Let's build smaller reactors that can be daisy chained to make to produce more power. Let's have a flexible pivoted strategy. I started my talk with there was this transition, and it was so important to be hands-on to shepherd and protect Artemis. Well, we need to make sure that nuclear programs don't just die in between administrations, so strategies need to be flexible. Learn from history. Don't just say, oh, we tried Jimo Prometheus in 2000, 500 kilowatts, it didn't work, so let's not try again. Let's learn what we can from Jimo Prometheus and then make it better. And then, of course, this is the last one, maybe controversial, it's my view. I think just like the terrestrial nuclear sector is completely commercial from start to finish, why shouldn't the space nuclear sector also be completely commercial? So that's kind of my view. So that's what I wanted to say. I hope I stayed within my time budget. I'm happy to take any questions now or later. And if you don't know what that song is, that just means you are too young. Thank you so much for your time.
Bhavya, great to see you.
Great to see you too.
Really appreciate it. You graduated here from nuclear engineering, right? In
did.
1990, 92. And in AeroAstro, we're currently undertaking a new strategic planning exercise. We've been doing that for a few months, and nuclear comes up a lot for surface power, for propulsion. Now, our current research priorities in the department, as published in our strategic plan, are the satellite constellations and swarms, humans and autonomy, and of course, decarbonization of aviation. Do you believe that in the new AeroAstro strategic plan, nuclear should make it into the top 3? And like you said, when you make something a true priority, you have to take something out. So that's my first question. My second one might be a little difficult, but I think everybody here is probably thinking about it. NASA headquarters. Spent a lot of time there. There's a lot of discussion about the role of NASA headquarters, what it is, what it could be, what it should be. Could you reflect on that a little bit?
Sure, the second one's a harder question. Okay, so on the first one, if we are to have a future in space, as I think I do, and as all of you, if you're in this room, you do too. I mean, you cannot do without power. You absolutely need, whether it's being on the moon or going to Mars or having, cyclers between Earth and Mars. I mean, it is at the heart of everything we want to do in deep space. Maybe we don't need nuclear for low Earth orbit or even, Earth orbit generally, although I think DoD would beg to differ on that. I think it is a critical enabler. It's a platform technology. It allows us to do everything else. So I would say, yes, it should be in the top 3. And of course, the question is, what do you take off? That's something that will take more discussion. I think one way to think about it is, MIT is where you are creative and have original ideas and new ways of thinking. So where is it that MIT has that comparative advantage versus where commercial entities are doing enough innovation? I mean, having looked at this area for the last many, many years, I know some of these things commercial parties cannot do. Deciding how to use high assay, low enriched uranium, which is about 20% enriched uranium, instead of highly enriched uranium, which is what we have traditionally used for our space nuclear systems, that is not an easily solvable problem. And governments have to do it, academia has to do it. So that's my answer to your first question. On the second one, I may change my answer after longer reflection, but my gut reaction is that there is, NASA has 10 field centers, as you all know, all over the country, and there are political reasons why they are in places that they are. Lyndon Johnson was trying to achieve some political objectives, and the infrastructure was built for the Apollo program. It no longer really applies as much. However, the centers now have political power, so it is not easy to erase them. Not that I'm saying that's needed, but I'm just saying that rational decisions can no longer be so as easily made. The role of HQ is to look at NASA across the board, to look at NASA in holistic ways, because in principle, they're not tied to a particular parochial interest, right? I mean, Marshall Space Flight Center in Alabama is the rocket center. That's where they build chemical rockets. Everything they will likely do, whether they want to or not, is going to be through that lens. Glenn in Ohio does power systems. Everything they do is through that lens. Johnson is a human space flight and ISS center. That's, for them, that's that. And anyway, I can keep on and on, right? Goddard and JPL are the science centers. So if there is to be a neutral point of view, it is likely going to come from HQ. And that would be the reason to actually have a strong headquarters. You all can always email me if you have any questions or comments or want to give me a new version of that cheat sheet chart.
Hi, thank you so much. As you talked through the history of nuclear, in-space nuclear development, you talked a little bit about the regulations, and I'm curious if you could comment on how regulations have changed recently, if they have changed recently to enable development, especially commercial development of in-space nuclear systems, and if not, what types of changes you think are necessary to foster that development commercially in academia and even within government.
Sure. So one really exciting change that happened was in 2019, 2020, and again, we have Scott Pace in the room, who was responsible for making that happen. So National Security Presidential Memorandum 20 replaced a previous presidential directive called NSD 25 something, I'm forgetting. So in the olden days, and this is from the 70s, there was no launch approval process system that worked for fission reactors. They were, even though they weren't created specifically for RTGs, they essentially managed the RTG. PDNSE 25, that's what it was. So NSPM 20 laid out, updated PDNSE 25, and what's really important and interesting and wonderful about NSPM 20 is that it is no longer a prescriptive regulation. It is not saying things like don't have a reactor go critical during launch. And again, it applies only to launch approval. So it's a very small piece of the whole cycle from development to launch to operation, right? So it's about the launch piece. And it is performance-based metrics. Make sure that the chance of exposing the public, total exposed TED for the public is a bit under 25 millirem, and that probability of that is 1 in 10,000. So it's just a wonderful way. And also the second amazing thing NSPM 20 did was it actually laid out a pathway for commercial systems. And a lot of companies like Xenopower and others came into existence because of that. So that is one of the most important things that has been done. And in fact, when I had the slide about what is new and different now, I should have added a fourth bullet, which is we actually have a regulatory pathway to launch nuclear systems. What we don't have is regulations for the pre-launch and the post-launch. And that's something we need to work on. Post-launch is a little bit easier, operating on the moon. We don't need to, again, there are probably outer space treaty implications, Article 9, which is about harmful contamination, but there's no public there to harm. So maybe we need to think about the post-launch differently. But pre-launch, we need to do a lot of thinking on how to make the regulations be, rational, and it shouldn't be, oh, we'll let you know when this works. So that would be my answer to your question. Thank you.